Chapter number 10, the amplifier power. In this chapter, we analyze the Class A amplifier. The common emitter amplifiers are most commonly used for the large voltage gain. They are produced the output voltage being for a relatively very small input signal. For few millivolts, we can get few volts output. Now, sometimes an amplifier is used to drive a large resistive load, such as the loudspeaker or drives of the motor. So these are the applications where need high switching current. The power amplifiers are applied over there. The main function is that it has large signal amplification and delivers power, which is the product of the voltage and current, and load basically goes to the load. Now, example, we can take a loudspeaker and have one high current flowing through the collector of the transistor because of high load current of the output transistor. Now we are interested in delivering the maximum AC power to the load while consuming the very little amount of the DC possible input voltage. So this one is the efficiency calls. So efficiency is the only the difference very ratio of the output power to the input DC voltage we are giving. The main disadvantage of the circuit is that there is overall conversion efficiency is very low, as the large currents means that considerable amount of power is lost in the form of heat. Okay, now the circuit diagram is like we give a small input signal to the voltage divider circuit. The transistor is always on so that the conduct during only one complete cycle of the input signal waveform is produced very minimum distortion. This means that a Class A amplifier configuration is ideal for operating mode because there is no crossover switchover of distortion. Now this is single-ended amplifier. Now the circuit is shown down below. We have to give the signal input, and for only half cycle, voltage divider circuit gives it goes to the base, and now at the output side, at the collector, we have output signal. These are the common formulas we use like VC, IC for the Class A amplifier circuit diagram, which we're gonna simulate in the simulation. We give the input over here, and this one is the base 1, base 2 voltage divider circuit over here for the base. This is the Darlington pair of transistor, and we are grounding the collector, so we have emitter connected to the load circuit of 5K. Now these are the graphs we obtain. The power. These are the graphs we obtain: the load power, dissipated power, and the clipping occurs. The clipping occurs after a particular peak. This one all clippings. Now this is the graph between the source power, the dissipated power, and the load power. This is the power flowing through the load 5K. Now in order to for proper biasing, we need a Q point which is neither in the saturate neither in the cutoff region. So for this circuit we find the Q point near like 12.6 and 6.3 as y-axis. Chapter 10, power amplifier power. Chapter 10, power amplifier. In this chapter we're gonna make a Class A amplifier. Just like a new project. Now name it as an amplifier power. Chapter 10, Class A. Select the directory in my saving file. Create a blank project. Now select schematic, page 1. Name the schematic page 1. Rename it. power. It's gonna study the power, so we get amplifier only. Now select libraries, EF, hot transistor. Select 3904, Q2M 3904. Add to the diagram. Select the analog components, capacitor, resistor. First we select resistor. That's the load resistor, cap collector resistor. We need one resistor for the emitter and one for the base. So we need 4 resistor. The base. One we need for the load. It's RL resistor. Now select the capacitor. We need for the coupling of output and input. Okay, for ground. What's grounding for the biasing circuit? One for collector bias and one for emitter bias, one for the base resistor, one for the input and one for the output. So we have 4 groundings. Select the source. We need AC source. So VAC, or we can use V sign. We are using DC for the biasing circuit. That's for the emitter bias. This one is for the collector bias. That's for the collector. That's our source. So we work as an input to our circuit. Use the capacitor for input coupling and output coupling. C input and C output. It's for the output for the load. Now you rename the components. Like this one is the VCC for collector. We connect and rename the components. Just move it. It's connected. It's done. It's on. We are making for amplifier. That's used for very large voltage and current applications. So remember that we need small value of resistance. here we have used a simple and stable emitter biasing because we want to design an application for the maximum possible unclipped output voltage, and we must be able to handle the heat dissipated in the transistor. So using a simple emitter configuration with very less value of resistance, so we can use for the high voltage and current amplification. We need to rename the components which we have done of the connecting circuit. This is the Vias for the output voltage. Need for plotting the graphs of V out. We need for the input to source P. This one is the load resistance RL, make it like 300. Coupling capacitance make it like 1 microfarad. This one like the collector bias circuit, we need 300 RC, and we have VCC of collector make as a 30 volt DC. So we make the VCC collector bias. It's common collector VCC. We need a VCS method here because we have a graph over here too. How much we have to want to bias this up. So we put capacitance 10 microfarad. We need a source of Vs of 0.2 volt amplitude and 10 k frequency. So V amplitude reading of 0.2 volt. Frequency of 10k. We are using class A amplifier. That's the VEE emitter voltage minus 5 volts, 4 volt, I'm sorry. That's the emitter of the transistor. We are biasing with negative 4 volt. Now in the source, we change the DF value. We need minus 4000 as the DF value of the source. You can add this one by double clicking on the source and just enter in the text. DF is the damping factor. Now add the simulation, chapter 10, amplifier power. And simulation from 0 to 1 millisecond. with the ceiling of 1 microsecond we can do that. Just the value of all the currents flowing up. Now go simulation, see the waves. Select the trace you want to see it. You want to see V out. That's our output voltage. So the quickly occur at same time on the both side of the peak. Select the VC and the Q1 minus Q1 minus VC. So voltage as collector minus emitter star, we are multiplying whole with the current flowing through the Q1. So this will be our dissipated power or WQ1. Now we want to analyze the load power. So we want power equals to VI, we know that, so will be V out star IRL. So voltage V out star the current flowing through the load resistance IRL. We have IRL here, so we product V out into IRL. This gives the total power at the load. The red line is the load power. Now we want to show the source power. Here is the damping factor. Now add the simulation, chapter 10, amplifier power. Simulation from 0 to 1 millisecond with a ceiling of 1 microsecond we can do that. Just the value of all the currents flowing up. Now go simulation, see the waves. Select the dress you want to see it. You want to see V out. That's our output voltage. So the quickly occur at same time on the both side of the bit. Select the VC and the Q1 minus Q1 minus VC. So voltage at collector minus emitter star, we are multiplying whole with the current flowing through the Q1. So this will be our dissipated power, or WQ1. Now we want to analyze the you want to see the load power. So we want power equals to VI, we know that, so we will V out star IRL. So voltage V out star the current flowing through the load resistance IRL. We have IRL here, so we product V out into IRL. This gives the total power at the load. The red line is the load power. Now we want to show the source power, so add a trace, the voltage as collector plus the emitter, and multiply with IC. So we want VCC, voltage at collector, VCC plus, we want multiply plus with the voltage of the emitter, VEE plus. This could be the voltage as an input. We want to multiply with that with the current flowing to the collector, IC Q1. As the Q1 means the collector at the Q1 transistor current. So we will multiply all these input voltages with the current IC Q1. So this will give us the source power. The blue one is the source power, red one is the load power, and the green one is the power dissipated. Switch. Now we want to analyze the Q point. So in order to analyze the Q point, we need to change our x-axis. So we need first analyze this one. How we want to change our x-axis so that we can see the Q point. The Q point is the point when you draw using your slope is equal to RC load. To make the Q point, we change the expression of x-axis. We need VQ C minus VQE. So on the x-axis we change the VQ C minus VQE. Change the expression. Remove the expression we have. Then we're gonna find the cube point, load time analysis. We're gonna change our x-axis variables. So in the x-axis we want VQC minus VQE, VQ1C minus VQ1E. This will give us the Q point, the point where the press were too much thick, and that's the line. So that we have to find maximum thickness. It's not nearby 12, nearby 12 it is also, like 12.62. And corresponding y value seems to be 62, like this. That's load line analysis. That's the 12.6, the thickest points we find it. The corresponding y value is 62 milliampere.